So hopefully you actually already watched the Knock the Block activity, saw it in class. If not, my quick overview is that we had a clay ball and a rubber ball. The clay ball was kind of this pinkish color. The blue was this rubber kind of ball. And they both have the same mass. Both have the exact same mass. They were picked up the same height above kind of their low point when they're just kind of hanging down at the bottom. And then they were each released. The clay ball hit and just kind of dead stopped right there on the spot. And the block wobbled a little bit, but it did not fall over, it didn't tip or anything. With the rubber ball hit, it actually bounced back. It bounced back up about a centimeter. So it started about 20 centimeters up. It ended up bouncing back up around 1 centimeter. And the block tipped over. It absolutely did. But both the balls were up the same height and they both have the same mass. And they both were pulled at the same angle, obviously, too. And I'll tell you that angle was actually 34 degrees. But that's what's kind of been given to us. And so the way this will work is I actually have the activity here and all the questions. We're going to go through all 10 of these together, but I'm going to be doing them for the clay ball and you'll be doing them for the rubber ball. You'll have both in your notebook, but I'm walking through all the steps for the clay ball. I actually have done parts 1 and most of 2 already. And so part 1 is just asking, what's the mass of the clay ball and the rubber ball? They both have the same mass. I plopped them on a scale. They gave me this in grams. I moved the decimal 1, 2, 3 spots to the left to turn it into kilograms. Golden, we're done. Part 2 is saying, what is the height the pendulum is raised? And then it says, use this height to find the potential energy in the ball. So we know the height. I've given that, it's 20 centimeters, and we want to find the potential energy of the ball. And this is the same for both, just kind of spoiling that. And so what we see then is that our potential energy is just mg delta y. And so we just have to plug in the given mass of one or both of the balls because it's the same, multiply it by g, and then multiply that by the height. But that height has to be turned into meters again. It absolutely has to be turned into meters. And so plugging that in to my calculator, as long as I didn't make a mistake, I get 0.170 joules. 0.170 joules. And following sig figs, it should probably be just 0.17 because this has 3, this has 2, this has 4. So our answer should have 2 significant figures. All right. So now we know the potential energy. We're done with 1. We're done with 2. Now, here's where we're going to deviate. You're going to follow along with me and do 3 along with me, but you'll have to do everything for the rubber ball solo style, kind of on your own, unless you want to phone a friend or something. So 3 is saying, determine the velocity of each ball right before it hits the block. So if we think about it, it's all potential when it's up here. It's all kinetic when it's about to slam in. And we know that energy is one of those things that's conserved. So we can really easily actually just apply conservation of energy. So we're just going to apply conservation of energy because energy is conserved. And so we know then that the potential at the top equals the kinetic at the bottom. And so I can just go ahead and write out mg delta y equals 1/2 mv squared. Nice thing here is that the m's kill each other off. They cancel out. We want to get v alone. I've multiplied both sides by 2, and then I would take a square root. And so I end up seeing here that the square root of 2g delta y, whoa, that was kind of an odd thing. Let's fix that there. Delta y gives us our velocity, kind of plugging in there. Then I have 2 times gravity times how high up we picked it up, so 0.200 meters, and don't forget the square root. That gives us a velocity of 2.0. Really nice, easy number there, meters per second. And it said, what is the velocity right before it hits? That's the velocity. we had all the energy was potential and it all became kinetic. And so for that to be conserved, this is how fast it must be going right before it hits the block. Excellent. So now let's look at 4. 4 says, determine the height the ball reaches after the collision, and then find the velocity of the ball right after the collision. So I'm seeing a height and I'm seeing velocity. That makes me think potential energy and kinetic energy. So we're going to probably end up setting some energies equal again here. Now, I'm doing the clay one. This one ends up being a little easier because the clay did not rebound. So after collision, there was no rebound. So no rebound. So our height, or maybe we call it delta y, the height is 0 meters. So if it goes up 0 meters, it gains 0 potential energy. If it gains 0 potential energy, that means it's stopped. So in 4, it's saying, what is the height it reached after collision? Well, the first part is gain no height, no rebound. And then the velocity after collision, 0. So the clay ball stopped. Now, because you need this, I will tell you that the rebound height for the rubber ball is right at 1 centimeter. We can actually just put that as 2 sig figs, 1.0 centimeters, but you can't leave it in centimeters, of course, right? So that'll help you with 4. So that's it. Let's look at 5. 5 tells us, determine the change in momentum. That's the same thing as the impulse on the block for both cases. Well, the impulse on the block is the same as the impulse back on the ball, because if the ball hits the block and changes the block's momentum, that means the block is pushing back on the ball and changing its momentum. So we can find the impulse on the clay ball. That's the same as the impulse on the block, and it will work the same with the rubber ball. So looking here, we have a couple equations from our equation sheet for momentum. We have, where even is it here? There we go. We have these two. We have that impulse is technically this thing. Change in momentum is force times time. But if momentum is also mass times velocity, that should mean that change in momentum is equal to mass times change in velocity. So we have 2 different options here, really, when it comes to solving this next part for 5. We want to find the impulse. That's the change in momentum. So we either have, let's use black, we either have that impulse is force times the time it acts, and we also have that change in momentum. Gotta love that auto shape there. Is also mass times the change in velocity. Now, in our case, we haven't been given any forces. We haven't been given any times. And so, unfortunately, this one's something that has too many unknowns for us, unfortunately. But we do know the velocity of the ball before collision, and we know the velocity of it after collision, and we know its mass. So we'll go ahead and use this second option really right here. So we're going to go with this guy. And I'll just write out that our change in momentum is its mass, so 0.08655 kilograms, times its change in momentum. So change in something is always final minus initial. And so since it stopped after collision, its final is 0 meters per second, minus its initial of 2 meters per second. Well, multiplying those 2 together, that gives me a value of negative 0.173, but rounding to sig figs, negative 0.17. And then we have kilograms times meters per second. So the units, really nicely for impulse, are kilogram meters per seconds. That's it. We're done with it, actually. So that was it for part 5 here. So now let's take a peek over at 6. Explain why the block reacts in the fashion it does in each collision. So essentially it's saying, why does the block not tip over with the clay, but it does tip over with the rubber? Explain why now. So this is less of a math thing. This is more of a, do you understand what's going on here thing? So, and I would encourage you that we could definitely think about this in terms of energy, but I want to look at this in terms of momentum. And so momentum is mass times velocity. And we're going from just a small clay ball moving to a much larger wooden block moving. And so we are correct in saying that the clay ball's momentum is all transferred. So all of it, I'm going to underline all transferred to the block. But it's not enough to knock it over. It's enough to make it wobble, but it's not enough momentum to get all that mass moving. It wobbles, but then there's this external force called gravity acting on this system here, right? And that's going to actually kind of pull the wooden block back, unfortunately. But it's not enough. But it's not enough to knock it over. All right, it's really just not. Unfortunately, it's not enough to knock the thing over. So that's it. Pretty simple. If you want to talk about it in terms of energy, we are losing energy. We absolutely are. Energy is being lost into deforming the clay itself. It smushes, essentially. There's all these little flat divots on the clay every time it hits that block. And so energy is being lost to that. And that energy is not being transferred then over to the block, which is kind of part of it. So what about 7 now? Draw a force vector diagram for the ball when it is just released from the highest point. Okay. Force vector diagram is the same thing as a free body diagram. It really is the same exact thing. So looking at 7 here, well, I'm doing the clay ball, so I should use this one. And there's my clay ball. And here is the tension line of the string itself. And we really have this force tension here, I guess, right? And then the only other force actually acting is gravity. So there we are. Force, gravity. That's it. That's all 7's asking you to do. Draw the free body diagram, and that is it. That is actually all there actually is to it. So what about 8 now? Looking over here at 8. 8 is where we want to find the tension in the string when the ball was just released. Okay, so to find the tension in the string, this is where things get a little dicey, because we have to remember back to not last unit, but unit 2 actually, which is kind of crazy. And so what I want to do is add to my picture here. I'm actually going to go ahead and redraw my picture even, or just copy it over here, kind of for simplicity's sake. So we can not have we still have the original free body diagram, but we can kind of mark up on it now. And so remember, there's kind of the pole that the string is attached to, and there's this angle theta here. And if I did like a vertical line going up, we'd have kind of the same angle here. So these are like alternate interior angles in kind of geometry terms. But what I can really do is I can say that, well, if tension is the black part going up here, that means the y component of tension is right here, and the x component of tension is right there. So we have these kind of components, and so what I've done is kind of built this nice, sweet little triangle here, and that triangle is going to help us out tremendously. And the thing that should be noted is the ball isn't just moving down, oddly enough, right? It's really not just moving down. We have kind of this neat triangle with our angle here. Oh, and I will kind of recap and mention that our angle is 34 degrees. And so we could use some trigonometry here then. We could go ahead and kind of do a couple things. We could say that, well, sine of our angle, that would give us the x part of tension over the total part of tension. And similarly, cosine of that angle would give us the Y part of tension divided by the total tension, just kind of using our triangle here again. So what I want to look at is note that the ball is not moving vertically down. The ball's moving actually around this circle. We could actually, like, if we had played it in slow-mo or something, you would see that there's actually this circle, and that was a terrible circle, but there's a circle that the ball is essentially going around. And tension is keeping it going in the circle. Tension is essentially this centripetal force. So it's not correct to say that the ball is moving down. The ball is moving tangent to the circle, which is kind of odd. And part of that has to do with the fact that gravity and tension in the Y direction balance each other out. These two kind of balance and oppose each other. And it's really this X part of tension that goes unopposed, all right, which is kind of odd here, and actually results in the ball kind of accelerating down towards the block. And so writing a little bit of that then to kind of see what this means, I would say then that the net force, the overall force in the Y direction, is the difference between the upward force of tension and the downward, that's why it's negative, force of gravity. And again, since the ball is not accelerating up or down, it's around the circle, we actually have zero acceleration here. This whole thing is zero. So this really just tells us that our Y part of tension is equal to the force of gravity, which is just m times g, and we know the ball's mass. All right, and so this is going to be maybe kind of helpful later. Actually, not later, but right now, actually, because what we can now do is, because I just saw it here, we can use this. We can use this because the goal for 8 is find tension. We don't want to find the Y part of tension. We want to find all of tension, not the Y, not just the X. We want all of it. And so what I'm going to do is I'm going to rewrite this part that I just circled. We're going to rewrite it, and we're going to rewrite it as force tension times cosine of the angle equals just the Y part of tension. And so what we can do with this is we can actually take this whole thing and plug it in. We can substitute it right there now. I don't know why I did that again. So we can plug it in right here. And so doing just that, I would write out, going down a line kind of for sanity's sake, that our force of tension times the cosine of the angle, and we know the angle, is equal to m times g. Now we know the angle, we know m, we know g, we know everything here but the force of tension. And part 8, is asking us what is the tension in the string. And so now we can just do a little algebra. That tension is equal to m times g divided by cosine of the angle. We can go ahead, we can plug into all this now. That tension is equal to 0.08655 kilograms times 9.8 meters per second squared over cosine of 34. Putting that into my calculator, I actually get 1.02 newtons. But we're looking here, and cosine of 34, that's 2 sig figs. 9.8, that's 2 sig figs. This mass is 4 sig figs, but since we're dividing and multiplying, we can only have 2. So this is going to simplify down to a clean 1 Newton. A lot of work just to get the number 1, right? So now, home stretch, we're on 9 and then 10. 9 is saying, determine the centripetal acceleration of the ball at this point. Well, throwback to Unit 3 now. This is a lot of review, actually. Force centripetal is equal to mass times the centripetal acceleration. All right? So what the heck are we being asked here? We're trying to find the centripetal acceleration. We want to get this AC right here. So to get that, well, we need to divide both sides by the mass. So our centripetal force over m is the centripetal acceleration. But what the heck is the centripetal force? It's the force keeping it going in the circle. Well, in our case, tension is the thing acting towards the circle. And so all we have to do is plug in 1 for our centripetal force, which is pretty nice, pretty beautiful actually that it worked out this way. So we end up plugging in now 1 Newton divided by this mass of 0.08655 kilograms gives us our centripetal acceleration. And that value is 11.5. But again, rounding to 2 sig figs, that should just round up to 12. So we'll just leave this as 12. You could have a decimal, you could not have a decimal. And since it's an acceleration, it will have units of meters per second squared is our centripetal acceleration. Excellent. Now, part 10, the very last part here, is actually kind of a description part here. Do both individual ball and block systems obey conservation of energy? So it's not talking about momentum anymore. It's talking about energy. And so we've already kind of answered this partially. Looking at the ball on the fall down, sure, it obeys conservation of energy. It has potential. It becomes kinetic. But since we're looking at the system, and let's choose to look at the system of both of them, I would say that the clay ball and block do not obey conservation of energy, and that's because some of the ball's gravitational potential energy was dissipated in mostly the deformation of the clay, but also in the form of heat and sound. And so we would say no in this case, and that is why. So I'm hoping you could write that. You can summarize that one. It essentially is no. But then I would like you to do the same thing, the same exact thing. You're going to answer all the same questions for the rubber ball, knowing that the angle is the same, and I have given you what the value is for the rebound height. All right, so thank you so much. Let me know when you have questions.